To my YouTube channel all about VLSI. In this particular video, let's continue with our decoder-based RAM verification where we are going to discuss the test cases. What are the test cases that we are going to use for the verification? So these are the test cases which we are going to use. The very first test case is RAM underscore random test. Basically, this is a random test which we are going to apply where we are going to have 32 number of write operations and 16 number of read operations. And after completing this random test, we are waiting for 30 cycles to move to the next test case. So the next test case is basically block boundary test, where we are going to give the starting and the ending address of a particular block. Like that, we are going to perform 8 write operations and 8 read operations. Just we are going to give the addresses corresponding to the starting and ending of a particular block. Next is RAM full sweep test, where we are going to provide all the 128 addresses which in a particular block. Like that, we are going to provide 128 write operations and 128 read operations. And next is RAM walking one data test. That means we are going to basically provide a pattern of data, which, like for example, let's say if I'm going to have a data like this, 00, let me write down over here, like 00. I'm going to have an address 1, 2, 3, 4, 5, 6, 7. So this is my first particular data. Next data will be shifted version, left shifted version of my 1, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, like this. So 1 will be shifted towards the left hand side. So this is nothing but walking ones. Okay. So where is this particular test case? Yeah, RAM walking one data test where I'm going to have the pattern of data like this 1, 2, 4, 8, so on. Okay. Next is walking 0. Same like walking 1, we are going to have walking 0 where 0 will be propagated towards the left hand side or shifted towards the left hand side. Next is we have tested walking 1 and walking 0 on the data. We are going to have the walking 1 and walking 0 on the address. Why are we doing this particular walking 1 and walking 0 on data and address? Because we need to have a check on stuck at 0 and stuck at 1 false. So if there is any fault or not, like stuck at 1 or stuck at 0 fault. So for that, we are going to have this particular kind of test. And next is same address override test. That means whatever the address which we have written that particular data, next data will also be written into the same address. So basically in this particular test, with using this particular test case, we are making sure that proper overwriting of data is happening at the particular location or not. And next is RAM toggle address test. That means we are basically toggling the enable signals. That means if we are writing the address, writing a particular data into a particular address, next immediately we are going to read the data from the same address. And again, we are going to write the data into that particular address. And again, from the same address, we are immediately trying to read. This is nothing but my RAM toggle address test. That means continuous or successive write and read operations can able to perform or not, we are basically checking. And next is RAM checkboard test. That means we are basically providing an alternate patterns like AA 55, and like this alternate patterns we are going to check. And this will be write operations will be 256 and read operations will be 256. And next is RAM block isolation test. In this particular thing, we are going to isolate a particular block with a one set of address, and remaining three will be reading, and only we are going to write down a particular data into a particular block, and we are going to read the data from other particular block. And next is RAM all zero test. We are going to write down all zeros in all the particular 128 uh, address locations. And next is RAM all one test, where we are going to write down all ones in a particular location. And next is RAM read before write test. That means here we are basically trying to read before even writing the data. And next is RAM constraint weighted test, where we are going to give weights to particular addresses. So this is the 15 test cases we are trying to verify on our decoder based RAM. And this is a clear explanation of each and every particular test case we have. So if you want, you can join in the channel group and you can access this particular document where we are where this is a clear explanation of each and every particular test case that I have already explained over here. And RAM walking 0, RAM same address override. This we have also seen, and RAM toggle address test, and checkboard test. So basically, it applies an alternating address data pattern, then its inverse to detect coupling faults between adjacent cells. So this is RAM checkboard test and RAM block isolation, where it is going to write a distinct set of addresses for block 0 and override block 1 and 3 with alternating data. And then it is going to read the data back from the block 0 for confirming the isolation. That means if we are going to write down a particular data from into block 1, and we are going to override block 1 and 3 with alternating data, and we are again going to read from the block 0 whether if we are performing the right operations in block 1 and 3, whether it is reflecting in another blocks or not. Basically, we are checking whether decoder is working correctly or not. And RAM all zeros and RAM all one, and RAM read before write, and RAM constraint weighted. So this is what we are going to give. Now let's see how we are going to basically check our design and how we are going to write down the test cases. Let us have a look. So I've created a base test where I've declared the virtual interface handles, which is write interface, write monitor, and read monitor. So only drivers and monitors should have the access to the interface. That's the reason I've declared all the four interface handles. And next I've declared the environment handle over here. Next, I've declared the two variables over here, which is address and data. So empty address and empty data, which is a dynamic array I've created. Now, within a new function, this test is also expecting few arguments: write interface, read monitor interfaces. After receiving this particular arguments from the top model, I'm going to copy it to the local copies. Next, I'm creating the memory for this arrays using the new, and here the size is 0. Basically, it's a base test. We are not going to drive any stimulus using this particular base test. So child classes, or whatever the test cases which we are going to develop further, those particular test cases will override this particular base test. And we are also going to have one function which is known as build underscore environment, where we are going to create the instance of my environment, and I'm passing whatever the interface or whatever the arguments my environment's new function is expecting. Those arguments I'm passing to it, and I'm calling the build function of my environment. And also I'm going to have a particular task which is known as body, which is basically a base test which is called directly and which is overridden in my child. And next is drain. So I've shown you, right, after performing a particular test case, how many cycles should I need before going to the next cycle. This is nothing but my drain. So by default I'm giving 30 cycles. And next is run. So this task will basically call the build underscore environment, and next it is going to start the environment method, and it is also going to call the body task, and it is going to call the drain task which is present over here. Next, I have also one more task which is known as do underscore writes then read. Basically, this particular task is going to have three arguments. One is address, data, and unsigned n. So this is going to call the run task of your environment, and it is going to pass the address, data, and number of n is basically, I will show you the RAM environment. So in the environment's RAM, we have a new function where, sorry, not new function. So what is this task environment.run? So we need to go to the environment's run task, and we will check it. What is the third argument which is present? So the third argument is number of writes. So that we are going to pass it as a third argument. And next is address. What is the address we want? That we are going to pass it. That is nothing but my read address. Next is number of reads, and next 0. 0 is nothing but randomize underscore transactions. I'm going to give it as 0. So this is how I'm going to next. And next is do underscore writes only. So this is only going to perform the write operation, where the first is address I'm providing. Next is what is the data, number of reads, and empty underscore address is the address I'm going to provide it. And 0 and 0. 0 is nothing but number of reads. Okay, so this is what I'm going to provide it over here. Number of reads. Here I'm not going to perform any read operation. That's the reason I've provided the third argument as 0 over here. Next is do underscore reads. So basically it is going to perform only read operation, where I've provided the empty underscore address as the argument, and next is empty underscore data is the argument. Next is 0. That is, I'm not performing any write operation. Address, and n is nothing but number of read. Next is do writes, then read different address. That means here this particular task is going to have few arguments. One is write address, next is write data, next is number of writes, read address, and number of reads. So I'm going to provide write address as first argument, write data as second argument, and number of writes as third argument. Now I'm going to provide read address as the third argument and number of reads and zero. So this task is going to perform the write operation, then also it is going to provide the read operation, and here we are providing the different read address. And in the previous cases, if you have observed, we were providing the same write address and read address, but this task is going to provide different write address and read address. So that was a base test class methods which are present, which we are going to use from the extended class or my child class. So the very first test case I'm going to have over here is I'm going to have RAM underscore random underscore test. So in the document we have seen, right? So RAM random underscore test. So this particular random underscore test is being extended from my base test. Okay. Now over here, I'm going to create two variables, number of writes and number of reads. Now here, this new function is also going to expect virtual interface handles, which my top model is going to provide it to me. And over here, I'm going to provide number of writes is equal to 32 and number of reads is equal to 16, because I'm basically following this particular document where the number of writes here is 32 and number of reads is 16, and the test class name is ram underscore random underscore test. Next, I'm going to refer to the base class new method, and I'm going to pass this to my base class super.new write underscore interface, read underscore interface, write monitor interface, and read monitor interface. And next, number of writes, the local copies will be copied to the 32 and 16. Next, I'm going to call the body task virtual. I'm going to keep it as virtual. And from here, I'm going to call the run task of my environment. And I'm going to pass empty underscore address, empty underscore data, number of writes, next address, number of reads, and one. You need to refer to the environment's argument, run task argument, then only you can able to understand. So first argument is write address, and I'm providing it. Whatever the user is giving the right address, I'm providing it. Next data, number of writes, number of reads, and all. Okay. Next, this is random underscore test. Next is block boundary. So in the block boundary test, I'm going to again call the new function, and in the task body, I'm going to declare address, data, and read address. Over here, address I've created 8 memory locations, and for data also I've created, and read address also I've created 8 number of locations. And you can see over here address is 0, and next address is 1f. This is one block. Next is 20 to 3f. This is another block. Next 40 to 5f is another block. Next 60 to 7f is another block. So like this, 4 block addresses I've given into 4 indexes. Next is 4 data items: AA, BB, CCDD, EE, FF, and 11 and 22. So like this, I've given all the particular 8 addresses. And next is I'm going to provide alternate read addresses. So I'm going to provide 00. Next is 1F. Next is 20 and 3F. That means whatever the addresses which I have provided as write address, same addresses I'm going to provide it as a read address, so that I can able to basically read the data which I've written into the starting and ending of my write, and that is my blocks. Okay. Next, I'm going to call the task which is known as do writes, then read different addresses. So this is the particular task which I'm going to call, and I'm going to provide address, data, number of writes, read address, and data. Read address and number of reads. So this task previously only we have seen, right? So what is going to happen? We are basically trying to write the starting address, starting data to the starting address, and data to the ending address of a particular block. Next, we are going to move to the second block, and we are again trying to write the data into the first position and the last. And next, we are going to have a task which is known as address underscore sweep. So in this particular task, or in this particular test case, what are we going to do? We are going to basically write down all the particular datas, all the into all the locations. So I'm going to have a for loop over here, which is going to have address of I is equal to I down to 6 down to 0. And data is what I'm going to do, complement of I7 down to 0. and read address is same as the write address. So I will be incrementing from 0 to 128, and all the particular addresses I'm basically writing complement of my I value. All the particular addresses will be written, and basically I'm going to call the do write then read task, which is going to basically perform the write operation into all the locations from 0 to 128, and then we are going to read the data from 0 to 128. Next is RAM walking one. So this I have told you, right? Uh, we are basically going to make each and every bit of a particular address to one. That is basically we are trying to make an one hot encoding kind of thing. So basically here my address will be equal to I6 down to 0. And next data is 0 1 left shifted by I. So I value will be incrementing and your 1 will be left shifting according to the value of your I. For example, if your I value, let me show you over here. So like example, if here the I value is equal to 0 1, that means 1 2 3 4 ones. I mean, the data value is initially 0 1 and I value is equal to 0. So left shifting will not be happening and your data value will be equal to 0. Next, if I value is equal to 1, then this data will be shifted towards the left hand side. Then your data value is nothing but 0 0 1 0. Depending upon your I value, your 1 will be shifted towards the left, and like this, you are going to make sure that every bit is 1 at a time. Not all the bits are 1 at a time, only one single bit is 1 at a single time. Okay. Next, we are also going to provide the read address so that we can able to read whatever we have written, and then we are going to call this particular task. And again, we are going to provide address and data information and all. Text is same to alternate walking zeros. So in walking zeros, we are going to make the complement. That's it. Where previously we are not applying this complement to the data, now we are going to apply the complement. And next is walking once on address bus. Whatever we have done with the data, we are going to do with my address. That's it. And over here, I'm basically making A0 I or operation with I7 down to 0. So to provide a particular unique data item to that particular address. And next is walking zeros. So the same thing which we have done with our data. That's it. And next is same address back to back. So over here in the same address back to back, what I'm going to do is I'm going to declare few variables, which is victims first data, second data, and A, RA, D1, D2. So I'm initializing everything. Victims is having 8 memory locations. First data is having 8 locations. Second data is having 8 locations. And A is only having 1 location. RA is having 1 location. D1 1 location. D2 1 location. Now, so this particular victims indexes I'm going to have first location as 00. So this is the first address. And next index is going to have 10. So why I'm taking 10 value? Because it is aligned in a particular block. 10 is basically an aligned address. And next is 2 is nothing but 1F. What is 1F? 1F is nothing but end of a block. So for that I'm going to take it. Next unique data I'm basically trying to, or unique address which I'm trying to get is 20. 20 is nothing but starting address of a next block. Next 3F. 3F is nothing but ending address of the second block. Next 55. 55 is nothing but alternate bit pattern. So what do you mean by 55? Why I am taking 55? Let me show you. So 55 you can see over here in binary, you can have the alternate bit pattern. So for getting this kind of pattern, I'm going to take the address as 55. Or I mean the address. For getting the alternate address, I'm going to have this 55. And next is uh, 70. 70 is nothing but my one of the upper region and 7F is the last address. So like this, different kind of addresses which I took. Next is data. So data also, again, A is nothing but alternate 10s and 55 is nothing but alternate 0101. So if you carefully observe, so A will basically give you alternate ones and zeros and 55 will give you 0101. And next is FF. FF is nothing but all ones, 00 is all zeros, and 0F is nothing but only lower nibble will be active, and F0 is nothing but upper nibble will be active. So 0F is nothing but only lower nibble will be active, and F0 means upper nibble will be active. And active in essence 1. And next is second data. Second data is basically the same thing I've given over here. Basically, second data of 0 will be 55 and second data of 1 will be equal to A. And second data of 2 will be equal to 0, 0. And second data of 3 will be equal to FF. Basically, I'm flipping the things. That's it. Okay. So victims, this is going to have the addresses, the unique kind of addresses I'm giving. And next is data also, the unique kind of data or patterns I'm going to give. So within a for loop, it is going to iterate for 8 number of times. What I'm going to do, A of 0, basically A is of only 1 bit. So A is nothing but it is an address. So A of 0 is nothing but victims of I. So victims of 0. And RA is nothing but read address. Basically it is also the same thing. And D1 is the first data and D2 is the second data. And I'm going to call the task which is known as do underscore write only. Previously we have seen, right? So this write only task is going to provide the address and the first data, and it is also having number of transactions as 1. Next, I'm going to call the do underscore write only, and I'm going to provide the same address. Next, I'm going to provide the second data item. Okay. And next, I'm going to call the task which is known as do read only, where I'm going to provide the read address. And here I'm going to get the data. And basically, what I'm checking is whatever the data which I have written previously is overwritten by the next data item or not. That is what I'm checking. And with different patterns of data, which I'm checking it. That's it. Next is RAM toggle address test. So in this particular RAM toggle address test, I'm basically toggling my different kind of addresses. So first address is I'm giving as 00. Next address is 2A. So let me show you. First address is 00. Next address is 2A. That means 00101010. Next address is 55. 55 is nothing but 01010101. And next is 7F. 7F is nothing but 0 followed by all. So this kind of addresses I'm giving. And next I'm going to give the data as C3. C3 is nothing but 1100 0011. And next is 3C. 3C is nothing but 00111100. So this is nothing but toggling of C3 only, right? So like that I'm giving the particular data items and I'm basically checking it whether this kind of addresses I can able to write and read. Next is checkboard pattern. In this, I'm going to provide the addresses and datas. First, I'm going to provide AA and 55, and I'm going to invert that particular address and I'm going to check it. So this is what I mean. I'm going to first of all provide the data AA and AA or 55, and next I'm going to provide the inverted version of that. That's it. And next is block isolation. So in this kind of block isolation, what I'm going to do is I'm going to provide the block address, next block data. Next, I'm going to provide the same read address. Next, what I'm going to do is I'm going to again start this particular for loop and I'm going to provide the block address and next block data. So this is how we are going to write down all the particular test cases and this is how we are going to verify it. So that's about this particular session. And in our next session, we are going to check how we are going to write down our top model and how we are going to perform the regression testing. So that's about this particular video. Thank you.